This is section 2.4, part B, zeros of polynomial functions. So when we're trying to find real zeros, there are a couple different methods we can help to narrow down where these zeros will be located. One method is Descartes' rule of signs, and this says if f of x is a polynomial with real coefficients, then the number of positive real zeros is equal to the number of variations in signs of f of x, or less than the number by an even number. And the number of negative real zeros is the same as the number of variations in signs of f of negative x, or less than that number by some even number. So if we take a look at this example, we want to see how many times we go from a negative to a positive and a positive to a negative. So if we look at our signs, I have a -3, and then we're going to go to a +2, so that's one sign change. Then I go from a +2 to a -1, and then a negative to a negative, so that does not change. So the number of variations we have is 2. So we know we have 2 or an even number less than that, so 2 minus 2 gives us 0. So we know g of x has either 2 or 0 positive zeros. Now we're going to find f of negative x. So we're going to plug in a negative x for each x, and then we're going to check out the change of signs. Now if we have negative x cubed, that's still negative x, and -3 times negative x gives me a positive 3x cubed. Negative x squared makes it a positive x, so this is a plus 2x squared. Negative times a negative x gives me a positive x, and then we still have that -1 at the end. So we want to see how many changes of signs we have. We have a positive, 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 then we change from a positive to a negative. So there is only one sign variation here. So we know g of x has one -0. If you were to actually graph this function, you would see that there is one -0 and there are no positive zeros. So we know that g of x has either 2 or 0 positive zeros, but in this case there are 0 positive zeros for this function and 1 -0. If we do this process again, remember first we're just checking for changes of signs. So I'm going from a negative to a positive, and then a positive to a negative, and then a negative back to a positive. So since we have 3 sign changes, there's either 3 or 1 positive zeros. Remember, you are going to subtract 2 each time because it's an even number less. Then we're going to do the exact same thing. We're going to plug in a negative x to see how many sign changes we have of g of negative x. So if we plug in a negative x to the 4th power, if you take it to an even power, it's going to become positive. So we have -5x to the 4th. Negative x to the 3rd power is just going to stay negative. You only change the sign if it's a positive, if it's an even exponent. So negative x to the 3rd is negative x to the 3rd. And I multiply that by 4, gives me negative 4x to the 3rd. Negative x squared is going to make that positive, so this is a plus 7x squared. Negative x times -2 gives me a positive 2x, and then we still have the +1 at the end. So we go from a negative to a positive here, but that's our only sign change. So g of x has one -0. We can also have complex zeros, so we don't have to just have rational and real zeros. We can also have complex. So just as quadratic functions can have real or imaginary zeros, polynomials of higher degree can also have zeros that are complex numbers. The fundamental theorem of algebra says a polynomial function of degree n, where n is greater than 0, has at least one zero, real or imaginary, in the complex number system. The linear factorization theorem: if the function has a degree of n is greater than 0, then f has exactly n linear factors. Now when we were breaking this down before, we wouldn't factor it any farther if they were non-reals, but now we are going to break them down. And so if there is a degree of 4, then we will have four linear factors. The conjugate root theorem: if a polynomial equation in one variable has a root form of a plus bi, then the complex conjugate a minus bi is also a root. So we need to write a polynomial function of least degree with real coefficients in standard form that has -2, 4, and 3 minus I as zeros. Remember when you put this into parentheses, so we write it into the linear factorization form. When you put it in, you change the signs. So since this is a -2, we put it in the parentheses, this will become a +2. We have a +4, and you put it in the parentheses, this will be x minus 4. We have 3 minus I. You need to put that in parentheses. So we have x minus 3 minus I. And that last theorem we wrote down, the conjugate theorem, says if I have 3 minus I, we also have 3 plus I. Now we just need to FOIL and then simplify, and then we're going to end up having to FOIL or distribute to finish solving this. So if we FOIL on the first two, x times x gives me x squared, x times -4 is -4x, 2 times x is 2x, and 2 times -4 gives me -8. Now we need to deal with the second part. So x times x gives me x squared. X times -3 plus I is going to give me minus x times 3 plus I. On the inside, we're going to have a -x times 3 minus I. And then last, plus 3 minus I, 3 plus I. Now if we combine like terms, distribute, and then we're going to have to FOIL again on this side. We're going to have x squared minus 2x. It is 2x, because when we combine like terms, it's -4 and +2 gives me a -2x, and then we still have that 8. On the right side, we have x squared. If we distribute that x, we're going to have -3x minus xi. If we distribute here, we're going to have -3x plus xi, because this is a negative and negative, which makes it positive. And then we are going to have to FOIL on this last part. So 3 times 3 gives us 9. 3 times I is 3i. This is -I times 3, which will give me -3i. And last, we have -I times I, which will give me -I squared. So if we simplify again, we have an x squared that's by itself. We have -3x and -3x, which will give us -6x. I have a -xi and a +xi, so those are going to cancel. I have a positive 3i and a negative 3i, so those are going to cancel. And remember, I squared is negative 1, so I can replace this with a negative 1. So we have a positive 9, negative 1 turns out to a positive. So we have a plus 10. When we get to this form, we are going to have to distribute or line these up and multiply. So if we go ahead and distribute, x squared times x squared gives me x to the 4th. X squared times negative 6x is negative 6x cubed. And then we'll have plus 10x squared. Now we're going to distribute that negative 2. So negative 2x times x squared gives me negative 2x to the 3rd. Negative 2x times 6x gives me a positive 12x squared. And a negative 2x times 10 gives us a negative 20x. Now we're going to distribute that negative 8. So negative 8 times x squared gives me a negative 8x squared. Negative 8 times negative 6 is a positive 48x. Negative 8 times 10 is a negative 80. Now we just need to combine like terms. So we only have one x to the 4th. I have negative 6x cubed, negative 2x cubed. So that gives us negative 8x cubed. We have a 10x squared, a 12x squared, and a negative 8x squared. That's going to give us a 14x squared. We have a negative 20x and a positive 48x. If we combine like terms, that's going to give us 28x. And the only thing that is the constant term is the 80. So our polynomial function of least degree that would have these zeros would be x to the 4th minus 8x cubed plus 8x plus 14x squared plus 28x minus 80. When we're factoring polynomial functions over the reals, every polynomial function of degree where n is greater than 0 with real coefficients can be written as the product of linear factors and irreducible quadratic factors, each with real coefficients. So if we take a look at this polynomial, we're going to write k of x as a product of linear and irreducible quadratic factors first. Then we're going to write it in the linear as linear factors. So first we're going to write it out with just the reals, and then we're actually going to break it down farther. And we'll have complex numbers. And then we're just going to list all of the zeros. So the first thing we need to do is if we graph that function, we're going to look for any zeros we think we can have. If we look at the graph, it looks like we have a 0 at x is equal to negative 5. So we're going to check that one first. So we use synthetic division. We bring down the 1. Negative 5 times 1 gives us negative 5. Bring that down, it's going to give us negative 23. Oh, I'm sorry, we skipped a 0, so hold on one second. We had to restart this because I didn't notice it first. We went from a degree of 5 to a degree of 3, so we skipped the 4th, so we had to add a 0 in there. So now if we bring this straight down, we have 1. Negative 5 times 1 gives us negative 5. When we add down, that's going to give us negative 5. Negative 5 times negative 5 is a positive 25. If we add down, that's going to give us 7. Multiply, add. And we do see that is a factor because the remainder is 0. Now we need to check for a different 0. So if we look at the graph, it also looks like we have a 0 at 2. Remember, once you find one 0, you can use the quotient from the first one to check for a second. So if we bring the 1 straight down, 2 times 1 gives us 2. 2 times negative 3 is negative 6. 2 times 1 is 2. and we do get a remainder of 0. So we do know that that is a factor. And if we check one more time at our graph, it looks like we have another 0 at 3. So 3 times 1 gives us 3. So we have zeros at -5, 2, and 3. And then you're left with x squared and a positive 1. So if we write that out, we have x plus 5. Because it was negative, we changed the sign when you put it in the parentheses. We had 2 worked, so we're going to have x minus 2. 3 was also a 0, so that's going to become x minus 3. And the quotient at the last one was x squared plus 1. Now we did not factor that down any farther, because if you would take that 1 to the side, it would become negative. And you cannot take the square root of a negative number and get a real number. So we are done with the product of linear where it's irreducible. If we do reduce this farther for the next part, because they want the linear factors so they can be complex numbers, we have x squared plus 1 is equal to 0. When you go to take the square root of a negative number, or when we go to factor this, remember that x squared plus 1 is the same thing as x minus negative 1. And when we go to factor that, negative 1 is the same thing as I squared. So we can factor that part. The square root of x is square root of x squared is x, so we have x and x. What multiplies to get I squared would be a positive I and a negative I. So if we rewrite this, our polynomial factor down would be x plus 5 times x minus 2 times x minus 3 times x plus 1 times x plus I times x minus I. So our zeros will be -5, 2, 3, negative I, and I. You can use synthetic substitution with complex numbers in the same way you use it for real numbers. So we can do this to help us factor polynomials in order to find all of their zeros. So we need to find all the complex zeros of the following polynomial. They do tell us that 2 minus 3i is one of the zeros. So we're going to use that with our synthetic division. So you bring the 1 down, and we're going to multiply. 2 times 2 minus 3i minus 1 gives us 2 minus 3i. When we add straight down, this is going to give us -4 minus 3i. Now you are going to have to FOIL. We have a 2 minus 3i and a -4 times -3i. So when we FOIL, this is going to give us -8 minus 6i plus 12i. -3 times -3 gives us a positive 9 I squared. But remember, I squared is equal to -1. So we can combine like terms. That's going to give us a positive 6i. And -8 with a -9 gives us a -17. When we add that down, that's going to give us a 3 plus 6i. Again, you are going to have to FOIL. When you're done, that's going to give you 24 plus 3i. If we FOIL again, that's going to give you a positive 13, and that gives you 0. So we do know that that is one of our factors. If we take the quotient from our first synthetic division and we use it for the second one, remember if 2 minus 3i is a 0, we also know that 2 plus 3i is a 0. So if we bring this straight down, we multiply, we have 2 plus 3i. When we add down, this is going to give us negative 2. When we multiply, this will give us negative 4 minus 3i. When we add straight down, this gives us a 6. I have to multiply the 2 by the 2 and the 3. When we add straight down, this is going to give us a negative 1. And we multiply, that's going to give us a negative 2 minus 3i, which gives us 0. Now we started out with a fourth power, so when we do division twice, we're going to end up with a second power. So this is x squared minus 2x minus 1. So when we factor this down, we're going to get x minus 2 minus 3i and x minus 2 plus 3i, and you're left with that x squared minus 2x plus 1, which you can factor down farther, but they will be complex numbers.